When I was a kid, I had one of these Air Hogs planes that was powered by a small plastic engine. This engine used compressed air as its fuel, and I remember pumping it up to high pressure with the small included pump before throwing it into the sky and never seeing it again, and ever since then I've wanted to build my own version but a little larger. This video is sponsored by Opera, so I started 3D printing some lightweight AR foil ribs in ABS plastic that will make up the internal structure of a wing. I could have used other materials like bola wood or carbon fiber, but those are more difficult to manufacture and wouldn't save a significant amount of weight as these ribs are very thin. Once glued to the carbon fiber spar, I glued a carbon rod to the leading edge and a carbon strip to the trailing edge, as the wing will be covered in a lightweight fill, so these will help hold the full shape. Now, I've never covered a wing like this before, so I had a quick read of the instructions. This stuff is very thin and delicate, so it creases easily, but on the underside it has a heat-set adhesive which can be ironed onto the wing structure, which is why they're printed from ABS due to its high melting point. Once signed onto the ribs, a quick blast with a heat gun will shrink the film down to create a smooth wing surface, but there are some issues, the first being the ribs at the wingtip bend inwards due to the tension in the covering film, and this tension also causes the air foil to shrink between the wing ribs, making an inconsistent profile along the wingspan. Plus, I may have held the heat gun in one position for a little too long, causing the covering film to melt. I just want to talk about wing design quickly, as this is the fourth air-powered plane I've attempted to build and fly. The first plane I built was the heaviest, but used a very similar wing to what I'm building now, though it was constructed from foam board, and despite the plane using a very inefficient engine, it actually holds my personal best flight time record of 16.5. May 20th, 10:07 a.m. Pawan Rajput. Half seconds, whereas my last air-power plane, which had a far more efficient engine and was much lighter, only flew for 8 seconds, which is partly due to it hitting a fence, but if the wing had a high lift-to-drag ratio, it may have cleared the fence. I've been trying to make these planes lighter and lighter while trying to make the engines more and more powerful, but what I haven't been looking at is the drag caused by the aircraft. The last wing I built was very light but also had a lot of drag, and May 20th, 10:07 a.m. Pawan Rajput. Because the thrust has to oppose the drag, the very little thrust produced by the engine struggle to get the airplane up to speed, so this new wing design uses a known error for profile, which with the right airspeed and angle of attack can achieve a lift-to-drag ratio of 60:1, so a little extra weight won't be much of an issue. And if you want to design a custom wing like this with your own aerofoils, I highly recommend checking out Onshape. I simply import the aero profile from atools.com, then with a few added design features, it's basically ready to print. These ribs are the same color as my t-shirt. To fix the issues caused by the covering film, I decided to use a thin sheet of bola wood to reinforce the leading edge. The stuff bends really easily, and if you take it outside in the British weather, it will bend even easier, so much so that I could bend it around a 3D printed mold of the wing and pin it in place until it dries. Once dry, it holds the curved shape of the leading edge, and I can print some new ribs with a small step where the bolster will mount to. I then gave the wood a few coats of bright orange paint to make it look nice, which gave me some extra time to build a new wing structure. This new wing is similar to the previous one but has much thinner ribs, as I'm hoping the bowls of wood will add some strength, as well as some thin carbon rods to prevent the wingtips bending inwards. Once the paint was dry, I glued the bolster wood onto the wing structure with some thin CA glue, and the wing was looking really nice with the orange leading edge and gray ribs. Then the covering film can be applied to check how the aerol profile turns out, which looks much better. Also, with the thinner 3D printed ribs, this wing is actually lighter than the first wing, and with 2 of these wings making up a 2M wingspan, it's over 3.5 times larger than the Air Hogs plane, so we need a powerful engine to fly it. Fortunately, I've been developing 3D printed air engines for a while now, and I've tried many different desk designs such as spring-operated inlet valves, common push rod valves, diaphragm-actuated pistons, and the latest design that uses a custom molded piston seal that expands under pressure to make the piston airtight, which is very similar to the Air Hogs engine. And this engine has been a huge step up in performance compared to my older designs, producing 350 g of thrust from an engine that only weighs 40 g. The engine is very simple with only a few moving parts. High-press air flows in through the top of the engine and is May 20th, 10:08 a.m. Pawan Rajput. Sealed by this ball bearing. Then, as the engine turns, a small pin on top of the piston moves the ball upwards, opening the valve and letting high-pressure air fill the cylinder, but this seal on top of the piston is a vital component to the engine's efficiency as it expands due to the pressure and seals against the cylinder walls. This causes the pressure to push the piston down, closing the ball valve and turning the crankshaft. Then, as the piston reaches the bottom, the air flows out the exhaust ports and the seal contracts, removing. May 20th, 10:08 a.m. Pawan Rajput. Any compression as the piston travels back up. Now, the airworthy version of this engine is slightly different but works exactly the same. It just has this 3D printed thread to attach to a plastic drinks bottle, and the air flows up this thin tube into the cylinder head. I also decided to buy a high-quality propeller to hopefully maximize the thrust output, and surely the fact that this propeller comes with its own socks must mean it's good. I know many of you are thinking, why don't I use CO2 cartridges instead of May 20th, 10:08 a.m. Pawan Rajput. Plastic bottles, as they can store far more pressure. Well, the CO2 cartridge is pressurized to about 800 psi or about 54 times atmospheric pressure, which is a lot, but its volume is very small at just 21 milliliters. So if we let the CO2 gas flow out of the cartridge to equalize at 1 atmosphere of pressure, we'd have just over AL of gas. But if we pressurize a 2L drinks bottle to 120 psi or about 8 times atmospheric pressure, we can store 16 L of air. This means we'd need 14 CO2 cartridges to equalize the storage.